Salutations, mini mathematicians. Welcome to Module 4, and we're doing 4.1b lesson today. We're going to be solving systems with graphing. So when we are solving a system, we are looking for one point or points, if there are any, that lie on both lines so that when we substitute them into the equation, it is a solution for both. So meaning it simultaneously satisfies both equations. So our purpose today is to be able to solve a system of linear equations by finding the point x comma y, or points, if there is one, of intersection, and know how many solutions a system has by investigating the equations. So what I want to look at is if there's one solution, the two lines will intersect at one point, meaning they're not parallel. Remember, parallel lines always have the same slope, so this just means if there's any two lines that have different slopes, they're going to intersect at one point. However, we have to be careful. If two lines have the same slope, we could have infinitely many solutions, or we could have no solutions. So if we have different slopes, we know there's one solution. If we have the same slope, we need to do a little more investigating to look at the y-intercepts to see if there's infinitely many or none. Note, if there's infinitely many solutions, the two lines intersect everywhere, and we show that by showing two pairs of arrows to represent the two lines. And if the two lines intersect nowhere, there's no points of intersection, hence no solution. We have parallel lines and there's no solution. Awesome, let's get started. For this lesson, you will want to have a ruler and two colors, or a pen and a pencil. That's totally fine, but it really does help the lesson today. So taking a look at 4.1b, solving simultaneous linear equations by graphing. Simultaneous just means at the same time. We're going to consider these two equations. And I like to always label the first one equation 1 and the second one equation 2 because that's going to help us with our graphing. And it says graph both equations on the coordinate plane below. If I'm taking a look at equation 1, I notice it's written in standard form. So I'm going to graph it using my x and y intercepts. So x-intercept, your y is 0. So taking a look here, my x-intercept is going to be 2 if I divide both sides by 2. So I can say x-intercept 2 comma 0. And my y-intercept, your x is 0. So that term would disappear and your y-intercept is just going to be 4. So 0 comma 4. So I can graph equation 1. X-intercept is at 2, y-intercept is at 4. I notice I'm going up 1, 2, 3, 4 over 2, which is the same thing as up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. And this is because I want my graph to be as accurate as possible, because the graph is going to be giving me my solution. Okay, so now I'm going to use my ruler. Really important, you do need to use some type of line tool. Go across the entire coordinate plane, put some arrows and label this as number 1. I'm going to label it on both sides. And then the second one, my y-intercept is at -2. My slope is 4, so I'm going to go up 4, 1, 2, 3, 4 over 1. Gee golly, I ran into the other line. That is excellent. There's my solution. So you want to graph until you hit the other line, and then you're good, because that's what you are looking for, your point of intersection. I'm going to label this one 2. And from here, it says state the coordinates x comma y of the point of intersection. Well, that is at 1 comma 2. And the next part asks us to verify. And remember, verify is a really important word. We're going to be verifying throughout this entire lesson. So when I'm asked to verify, I need to substitute the point that we found, 1 comma 2, into both equations to satisfy both of them. So here I'll have 2 times 1 plus 2 is equal to 4. Order of operations, multiply first, and 4 equals 4. Awesome. And the second equation, I'm going to substitute 2 in for y, 1 in for x. 2 equals 4 minus 2, and yes, 4 minus 2 is 2. Remember, when you are verifying, you're not doing any inverse operations to both sides. You're just simplifying down to make sure you get the same number on each side. Perfect. So the example above, the point of intersection is the solution to the system of equations for 2x plus y equals 4 and y equals 4x minus 2. The solution or solutions to a pair of simultaneous linear equations is all pairs, if any, of numbers x comma y that are solutions to both equations. That is that x comma y satisfies both equations, and when solved graphically, the solution is the point or points of intersection if there is one. So let's talk about what we could have. So I'd like you to draw 5 quick little coordinate plane sketches so we can talk about our possible situations we could come across. So the first situation we could come across is no solution. If we have no solution, that means there's no points of intersection. So that's going to be 2 lines that are parallel. Okay, another situation we could have is we could have one solution. One solution meaning the 2 lines intersect at one point. They have different slopes. They could intersect anywhere. It just means that they're going to have different slopes. So there would be my one solution, the point of intersection. Another situation we could have is infinitely many. I'm going to use the infinite symbol. It looks like a 3D potato chip. Infinitely many. If we have infinitely many solutions, that means we have infinitely many points of intersection, which means the 2 lines are in fact the same line. And we show that by showing 2 pairs or 4 total arrows on the same graph, showing that there's 2 lines graphed on the same line. Another situation we could have is if there's more than 2, if it's more than a pair of linear equations, we could have 3, and soon we will have 3. So if we have 3 lines that all have one common point of intersection, then this is still one solution. However, if we have 3 lines and they don't all intersect at one spot, let's say it goes like this, and like this, and like this, there's no one point that intersects all 3 lines. So this would be considered no solution, because remember, it has to be one point on all 3 lines simultaneously. So for the system. Okay, so number 2 says graph the following system of linear equations and is 4, 2 a solution. Justify your answer algebraically. So again, I'm going to label these as 1 and 2, and this helps us organize our work. And then if you graph one line incorrectly, or if when you're going back to check if your graphs are correct, it makes it a lot more simpler for you to know which one you are checking. So equation 1 is written in slope-intercept form, y equals mx plus b. So I'm going to start with my y-intercept, -5. I'm going to go up to right 1. Before I continue graphing, I'm going to double check. Positive slope, good. I'm going to keep on graphing because I need this to be as accurate as possible. I'm going to grab my ruler here and label this as 1. Okay, now I'm going to graph equation number 2. I'm noticing with equation number 2 is written in standard form, so we could graph our intercepts, or we could use our ratios for slope. So remember, our slope ratio is -a/b, so this would be -4/5. And our y-intercept is going to be c/b, so that is 25/5, which is 5. So I'm going to graph that way. I'm going to graph my y-intercept at +5. And then I'm going to go down 4, 1, 2, 3, 4, and to the right 5. 1, 2, 3, 4, 5. And notice I will see that I'm intersecting here. And the point they are like, oh, we should label this. Good job, good job. Oh, with the point we're asking about is 4, 2. So 1, 2, 3, 4, up 2. So if we look at 4 comma 2, 4 comma 2 doesn't actually lie on either of the lines. So a lot of times, especially if you're not being as accurate with your graphing, you might say, oh, well, it's really close to here. I'm just going to say that's the solution. That is not okay here. We need to be as accurate as possible. And this is justify your answer algebraically. So I'm going to make a t-table to organize my work. You're going to be using t-tables a lot this module to keep our work nice and organized. I'll have equation 1, y equals 2x minus 5. Remember, the point we are verifying about is 4 comma 2, xy. So we have 2 equals 2 times 4 minus 5. And if 4 comma 2 was a solution, it means it lies on the line and satisfies the equation. So we 2 equals 8 minus 5, but 2 does not equal 3. So this is false. And you always want to verify both equations. 4x plus 5y equals 25. 4 times 2 plus 5, x is 4. 4 times 4 plus 5 times 2 equals 25. 4 times 4 is 16. 5 times 2 is 10. And this is 26, which does not equal 25. So this, again, is a false statement. So algebraically, when you substitute in x equals 4 and y equals 2 into both equations, neither results in a true statement. So the point 4 comma 2 does not fall on either line. So is 4 comma 2 the solution? No. 4 comma 2 does not lie on either line. It is not the point of intersection. So as you can tell, some systems, if the point of intersection are integers like 4 comma 2, negative 8 comma 3, the solution can be found graphically. However, not all systems can be solved graphically, and that's what we'll be getting into as we continue with our module. Okay, so let's take a look at the next page. Let's read the directions because directions are super important. It says graph the given equations on the same coordinate plane and find the solution. Verify that the solution satisfies both equations. So I'm going to do 3 and 5 with you, and then you're going to do 4 and 6 on your own. Okay, so let's take a look at number 3. I'm going to label them 1 and 2. And from here, taking a look at equation 1, we could rewrite that in slope-intercept form if you wanted to, since it's just subtracting 2x from both sides. This is y equals negative 2x plus 10. You could also look at your ratios, or you could find your x and y intercepts. So I'm going to graph this. 10, oh, thank goodness that y-intercept's there. Down to right 1, double check. Yep, we have a negative slope. In this lesson, they just really liked the slope of 2, huh? Graphing. And I dropped my ruler, so I'm going to grab that. The gravity, it's strong in here. The force. Okay. So we are going to make our beautiful line with your line drawing tool. Now we need to graph equation 2. And this one, I just have to subtract x on both sides, so I'll just rewrite it in slope-intercept form. Y-intercept is 8, so 5, 6, 7, 8. Down 1, right 1, down 1, right 1. Woohoo! We landed on the other line. We found the point of intersection. So I'm not going to worry about continuing to graph this line because I found what I was working towards. The whole goal was to find the point or points of intersection if there is one. So our solution here is we go right 2 and up 6. So that means 2 comma 6. And I love giving it a little bit of flair around here. Write your answer as an ordered pair. Give it some flair. And now we have to verify. So whenever we verify, I like to use a t-table to keep my work nice and organized because I have verified in the same equation twice. Silly. So don't make my same mistakes. You're better than that. So equation 1 is y equals negative 2x plus 10. and your y is 6, your x is 2. 6 equals -4 plus 10, and -4 plus 10 is 6. Woo! We got it right. We got it right. Okay, let's check number 2. You can use the original equation or your equation in slope-intercept form. If you use your equation in slope-intercept form, you are running the risk that you made a mistake algebraically. So it probably is better to use the original. So let's take a look using the original this time. 2 plus 6 is 8, and 8 is equal to 8. Awesome. Woohoo! So that is graphing the system and then verifying algebraically. So I told you we'd do 5 also together. So number 5, I'm going to label these 1 and 2. And looking at equation 1, the only thing to write in slope-intercept form is adding 2x to both sides. So y is equal to 2x minus 1. I'm going to graph this by graphing your y-intercept at -1. I'm going to go up 2, right 1, up 2, right 1, up 2, right 1, down to left 1, and of course use a ruler. If you are not using a ruler or a line tool for this lesson, it's going to be really difficult for you to really find the point of intersection sometimes. And our second one, y equals 2x plus 4, I'm already noticing I have the same slope and different y-intercepts, so I know my system is parallel. But I still have to graph it because that's what it asked me to do in the directions. So here we go. I think that's enough because I already know it's parallel. A quick tip when I'm graphing parallel lines, I'll line it up with the line I already graphed that's parallel, and then just translate my ruler over so that it really looks super parallel. Oh, many mathematicians, Miss Barr made a big mistake. She has been forgetting to label. I guess because I have been using colors to coordinate, that's helpful, but you still want to label. So if you had looked at your paper and you're like, ooh, I don't know which line's which, labels will super help you. Okay, so the last thing we need to do in step 5 is to verify, but notice we have no solution, so we still need to write that down. So this is no solution. And to verify, we're not actually going to substitute in, we're just going to write reasoning y. So we're going to verify with our reasoning, so we can say lines y equals 2x minus 1 and y equals 2x plus 4 are translations of each other, and hence parallel. Therefore, and if you didn't know, there's a symbol for therefore. It's these 3 little dots. So you might see that in the notes, and super mathy. Therefore, the lines never intersect, and the system has no solution. So if you do find a point of intersection, please verify using both. If you do not have a point of intersection or infinitely many intersections, give a justification as to why that happens. Okay, so you're going to work on 4 and 6. You're going to work on 4 and 6 and pause the video and we'll go over it as soon as you're ready. Okay, let's take a look at this. On number 4, taking a look at 4, I graphed equation 1 and equation 2. They're already written in slope-intercept form, and I graphed them until they intersected, which was that 2, -4. So 2, -4 is the solution, and when I verified, I got a true statement for both, which was awesome. And on number 6, notice we have 2 lines that are actually the same line. I graphed those using 2 pairs of arrows for 4 total arrows. And I wrote my answer as infinitely many solutions, so don't forget to write your answer. And I said that lines x plus y equals 3 and 3x plus 3y equals 9 simplify to the same line and intersect everywhere. Great job. Okay, so we are going to keep going and we're going to summarize everything we just talked about in a nice table. So taking a look at this table, it says, what is it about the structure of the equations in a system that leads to one solution, infinitely many solutions, or no solutions? And complete the table below. So this is going to be important for the rest of our module. So one solution. We have the type of solution, explain the structure of the equations, and we're going to always explain in y equals mx plus b because that is the most efficient way to graph. We're going to have an example of a system in slope-intercept form, and then we're going to have a quick little graph. Okay, so one solution. We know that the graphs are going to intersect. There's one point of intersection, which means all you need to have for one solution is different slopes. Different slopes. So that means the slope of the first one is not equal to the slope of the second one. So an example could be, and we're going to give examples that we can graph over here. So I'm going to have equation 1 be y equals negative 2x plus 1. And I will graph that over here. So I'm going to go to plus 1. I'm going to go down 2 over 1, down 2 over 1. Graph that. And all I need is a different slope. You could have the same y-intercepts if you want, but you just have to have different slopes. So my equation 2, I'm going to say y equals 1/2 x plus 5. So I'm going to go to plus 5. I'm going to go up 1, right 2, or down 1, left 2, left 2. And we can see that they do intersect at one point. So that's equation 2, and that's equation 1. Cool, let's take a look at the next one. The next one says no solution. That means that they intersect nowhere. They will never intersect, which means parallel lines. So we know that this is going to have same slopes. So the slope of equation 1 is going to equal the slope of equation 2. We're going to have different y-intercepts. So that means the y-intercept of equation 1 needs to be different than equation 2. Notice they are translations of each other and parallel. Okay, so let's take a look at an example. So equation 1, I'm going to use y equals 4x plus 4. So go to 4 and up 4. 1, 2, 3, 4 over 1. 1, 2, 3, 4 over 1. I'm going to graph this line. And my second equation, remember we need the same slopes but different y-intercepts. So I'm going to use y equals 4x minus 1. So I'm going to go to negative 1, and then I'm going to go up 4. 1, 2, 3, 4 over 1. Up 4, 1, 2, 3, 4 over 1. And I can clearly see that these are going to be parallel. Can justify that using the equations. And I can see that with the graph. Okay, so the last situation we may have with a pair of simultaneous equations is infinitely many solutions. So infinitely many solutions, remember that means they intersect everywhere. So we are going to have the same slopes equal slopes value. So m1 is equal to m2. And we're going to have equal or same y-intercepts. So the first y-intercept is going to equal the second y-intercept. A lot of times when we are looking at these, we will write them in different forms, not just in slope-intercept. But remember, this does give an example in slope-intercept form. So I'm going to use equation 1 to be y equals x minus 1. And I'm going to use, I'll graph that. So -1, up 1, right 1, up 1, right 1, up 1, right 1. And there's equation 1. And I'll say equation 2 is also y equals x minus 1. And all I have to do is add extra arrows here. I know, Mrs. Barr, you didn't use your line tool, but I did a pretty good job. Okay, so this is a great little cheat sheet for you to go to and help you remember the different systems. And since we talked about the structure, now we're just going to look at the structure and figure out how many solutions there are. So the directions say for number 8, without graphing, determine whether the following systems of linear equations have one solution. Remember, m1 does not equal m2. No solution means they're parallel. So m1 equals m2, but b1 does not equal b2. Or infinitely many solutions, meaning they have the same slopes and the same y-intercepts. Because they're the same line, they intersect everywhere. Okay, and state the reason why. Por qué? You gotta explain yourself. Okay, so I'm going to do A with you, and then you'll be able to do B and C by yourself. Okay, so I'm looking at equation 1 and equation 2. I notice equation 1's not written in slope-intercept form, so I'm going to write it right below it. Y is equal to -2x plus 8. So now when I'm comparing the slopes, I say 2x and -2x. So I know that there is going to be one solution. That's my number one answer, so I'm going to give it some flair. And I'm going to say why. The lines have different slopes. Therefore, I'm going to use those 3 little dots for therefore. Intersect once. And 1 point of intersection means 1 solution. Awesome. I love you to look at B and C. Pause the video and we'll go over it in just a second. Okay, let's take a look at B and C. So taking a look at B, here I use the ratios because I had a coefficient of y here. I used the ratios to look at what the slope and y-intercept are from standard form. And I saw that the slopes are the same, but the y-intercepts are different, meaning they're going to be parallel lines, so no solution. The lines have the same slope, -3/2, but different y-intercepts. The lines are parallel, therefore they never intersect. And the number of intersection points is a synonym and helps you figure out how many solutions. C, when I rewrote this second equation, I noticed if I divided every term by -2, I got x plus y equals 5. So I noticed these are written the same. They're the same equations. So this is infinitely many solutions. The equations simplify to the same line and therefore intersect everywhere. Remember, the number of intersections is equal to the number of solutions. Great job, mini mathematicians. Okay, so we have one more page left. I would like you to be working on number 9, and we're going to go over it in a second. So this is the first equation in the system. This is equation 1. And then you're going to write the second equation in slope-intercept form so that the system now has only one solution. One solution, meaning that they need to have different slopes. And then you're going to look at write a second in standard form so the system has no solution, and you're always using this first equation as your original equation. Some of them, the answers will vary, so don't feel like you can only find one solution. And we'll go over these in just a second. Please pause the video and we'll go over the solutions. Okay, let's take a look. So number 9, the first thing I did with number 9 was I looked at the equation given to me in almost standard form, where it did need to be simplified a little bit. And I looked at the slope to be -3/2. I looked at the y-intercept to be -3, so 0, -3. So when I needed to write a second equation in slope-intercept form, and with only one solution, we needed different slopes in any y-intercept so that they're going to intersect at one point and therefore have only one solution. So your answers are going to vary. Your m value needs to be any number not equal to -3/2, and your b value can be any number. It can totally be -3 if you want. So here are some examples. I said y equals 5/2 x plus 2, y equals -3x minus 11, and so on. For b, we needed a second equation in standard form so that the system has no solution. Remember, no solution means we need equal slopes and different y-intercepts. So the lines never intersect, hence there's no solution. So your answers will vary, but if you start with slope-intercept form and then rewrite into standard form, notice y equals -3/2 x plus b. This b can be any number except -3. So it could be 5, it can be -2, it can be +3, but it cannot be -3. So my example, I decided to use y equals -3/2 x plus 4. And then since this needs to be written in standard form, remember standard form is ax plus by equals c, where a, b, and c, there's no fractions, there's no decimals, and a has to be positive. So we can say b and c can be integers, and a has to be a whole number. So I needed to get rid of my fractions, so I multiplied everything by 2, and then brought my variables all over to the left, added 3x. I had 3x plus 2y equals 8. And remember, you can also check your ratios for the m and the b values. So your slope should always be -3/2. So everyone should have 3x plus 2y here. And this equals number on the other side can be any number except for -6. Because if this was -6 and I divided by 2, I'd get -3. Awesome. So this can be 3x plus 2y equals c, where c can be any number but cannot be equal to -6. Okay. So the last part, C, asks you to write an equation in standard form. So the system has infinitely many solutions. So there's only one answer here because your answer has to be in simplest form. So we need to have equal slopes and equal y-intercepts, therefore having the same line and hence having infinitely many points of intersection. So we have infinitely many solutions. So here, since we need this in standard form, it does have to be simplest form, meaning all these have a common factor of 2, so I need to divide each term by 2 to get my equation. Wonderful. Okay, so number 10 asks you to graph the system of 3 equations and state the solution. So what we're going to be doing is you're going to graph all 3 of these. You might want to rewrite them in slope-intercept form or graph them in standard form. Be as accurate as possible and make sure to label them. Pause the video and we'll see how you do. Whoops. Pause the video and let's see how you do. Okay, so let's see how we did. Y equals 1 is a horizontal line, so that's my equation 1. My second equation I rewrote in slope-intercept form, so I had a y-intercept of 2 and then a slope of +1. And my third equation, I started to use the ratios, but I noticed my y-intercept wasn't an integer. Oh no! So I decided to find my x-intercept and then move slope amount. So I did that. And so I found that my x-intercept was 1, and then I moved slope amount, which was -1/2, so down 1, right 2. I noticed I wasn't getting over to the point of intersection, so I went up 1, left 2, and I landed on -1, 1 is the solution, the point of intersection, and lies on all 3 lines. So if we did plug in -1, 1 into all 3 equations, we would get a true statement. Great job, mini mathematicians. Keep up the awesome work. I will see you next time.